Hello everyone, welcome to Chapter 7. The theme of this chapter is Building Blocks of Integrated Circuit Amplifiers. In this chapter, we will learn about the basic principles of IC amplifier design. We will discuss how IC design differs from discrete circuit design and explore current sources, current mirrors, and gain cells. Understanding these concepts is crucial for designing efficient IC amplifiers. Let's begin by looking at the key topics covered in this chapter. In Chapter 7, you will learn the following topics, including, first, the basic integrated circuit, IC, design philosophy and how it differs from that of discrete circuit design. Second, how current sources are used to bias IC amplifiers, and how current mirrors are used to replicate the reference current generated in one location at other locations on the IC chip, where bias means to provide a working point to an amplifier, and a current mirror is one of the important techniques to provide multiple current sources for some amplifiers on the same IC chip from a refer current source. Third, the basic gain cells of IC amplifiers, namely the CS and CE amplifiers with current source loads, where the CS and CE are the basic units to build an amplifier that you need, maybe higher gain or lower output impedance, and so on. And fourth, how the CG and CB amplifiers act as current buffers. Sometimes you need a current buffer to convert or transfer a current signal. Fifth, how to increase the gain of the basic gain cell through the principle of cascoding, where cascoding is a method of connecting multiple basic gain cells in series to achieve high gain or high impedance. We will also explore the cascode current source, which is widely used in IC design. Sixth, analysis and design of the cascode amplifier and the cascode current source in both their MOS and bipolar forms. Seventh, how the IC source follower differs from the discrete version. Finally, we will introduce some advanced analog circuit techniques that improve current mirrors and amplifier performance. Actually, current mirror is not a perfect current source. So many techniques are proposed to compensate for some electrical characteristics in some applications. Next, I will roughly introduce the IC design philosophy. IC design is Taiwan's most important industry, and Taiwan's technology in the IC industry far exceeds that of other countries. In this section, we will introduce the concepts of IC design. IC fabrication technology is very different from general discrete circuit design. Integrated circuit fabrication technology imposes constraints on and provides opportunities to the circuit designer to cope with the constraints and take advantage of the opportunities. IC designers have over the years invented and continue to invent many ingenious techniques, and a distinct philosophy has emerged for the design of integrated circuits. In the following, we provide a brief summary of the important constraints and opportunities, and the major features of the IC design philosophy. First, the biggest challenge in IC design is the limited chip area, and good designs are economical in using silicon real estate. This area constraint dominates the transistors, which are preferred over resistors because they take up less space. Transistors on an IC can be made small and cheap. Thus, while the designer of discrete circuits aims to minimize the number of transistors, this is not the case in IC design. Second, unlike the designer of discrete circuits, who is limited to available off-the-shelf transistors, the IC designer has the freedom to specify the transistor dimensions. As well, IC technology allows the fabrication of arrays of transistors having dimensions of specified ratios capable of being realized with great precision. These factors make IC design very different from discrete circuit design. Third, resistors, especially those with large values, occupy large silicon areas and should generally be avoided. Instead, constant current sources implemented with transistors are used in applications such as biasing, or in place of the load resistance of a transistor amplifier. Fourth, although small value resistors can be fabricated on an IC chip, their absolute values cannot economically be made precise. Rather, arrays of such resistors can be made to have relatively precise ratios. Fifth, chip area considerations also make it impossible to fabricate large value capacitors, such as those used for signal coupling and bypass in discrete circuit amplifiers. As a result, IC amplifiers are all directly coupled and use clever techniques to establish signal grounds, as we will see later in this chapter and the next. Sixth, small-size capacitors, such as those in the picofarad and fraction of a picofarad range, are easy to fabricate in IC MOS technology with very precise ratios. Capacitors of this kind can be combined with MOS amplifiers and MOS switches to implement a wide variety of signal processing functions, such as filters. 7th, to pack a large number of devices on the same IC chip, thereby reducing system size and cost while improving reliability. The trend has been to reduce the device dimensions. 8th, currently, the vast majority of analog integrated circuits are designed using CMOS technology. However, BJTs are still used in special analog applications, such as high-quality general-purpose op-amp packages. In the next section, we will introduce the most important IC biasing technique based on constant current sources. Since there may be many amplifiers or circuits in an IC chip that need to be provided with different bias currents, current mirrors that can provide multiple sets of current sources are often used in IC design.